Alright, today, chapter 6, sampling and estimation. Yes, all four of you, and the one, move to the one, MacBook. No, come here, up front. No, you come here. Alright, sampling and estimation is the basis of statistics, the foundation of statistical analysis. It's all about data, but in the real world you can't get all the data all the time. In the real world you get only a small portion of the data. That small portion is the sample. The full data would be the population. So, sometimes you need to get a sample or take a sample. If that's the case, you need a sampling plan. And the plan is how you're going to go about it. How, or the approach used to obtain. I'm still waiting on it. How you're going to obtain the sample. For example, if you want people here in samples for people living in the city, are going to stand in front of the university and take a sample? Are going to stand at the mall and take a sample? Are going to stand at the riverside and take a sample? Are going to phone call? Are going to send email messages? How is it going to be done? So, when you have a, guys, hey, welcome, class began about 4 minutes ago. You're going to get separated and join her soon, okay? So, if you do a sample, you need to have an objective. Well, what's the goal? What's the objective? What are we trying to do? Next, you need a target population. Are we going to target students? Are we going to target students in the university? Are we going to target girls only? Are we going to target city people? Are we going to target villagers? Are we going to target all Cambodian people? Are we going to target Asians? Are we going to target foreign tourists? You need to understand what's the goal and what is the target. And then you need a population frame. In other words, where and how you're going to get the sample. Are you going to get it by people walking on the street, or are you going to get the full list somehow? Here in the university, it's very easy to get the complete list of all students. It's very easy. So if it's about students, we get it on the list. And finally, the operational procedures. What you're going to do. Who will be responsible? When is it going to get done? How is it going to get done? How are you going to ask the people? Are you going to write their answer, or you give them a chance to write their own answer? How anonymous it is. You need to figure out different details. They give you a little example. We can skip the example. Sampling methods. You can do a sample in a number of different ways. Number one is judgment sample. You exercise a judgment. You use experience and you use expertise. They call it expert judgment. So usually, if you got a let's say you want to, do analysis of obesity, you're going to go to the doctor, and the doctor is going to tell you, oh, you go here, or you go there, you do this, or you do that. You can interview or sample these people. You don't have to sample those people. Or if it's for school, you ask teachers, okay? So basically, you find an expert. The other one is convenience sample. Convenient sample is you basically go in front of the supermarket, or you go in front of the store, or go in front of the restaurant, or go at the riverside. You go some nice place, and it's quick and easy. Another quick and convenient, easy way, you shoot an email to 1,000 people and hope somebody responds. So, you select it on the basis of making it easy, but just because it's easy doesn't make it good. A lot of times, because it's easy, it's actually not a good sample. And finally, you can do some probabilistic sampling. You use a simple random sample. Well, here's an example over here. An example over here is we can use all student IDs with number 14. Well, that will be, if they begin with number 14, that's a bad sample because it picks only, 30-year students, right? That's not a good sample. But a nicer random sample will be all students whose ID ends in 5. If yours ends in 5, if yours ends, whoever ends in 5. So the last number is fairly random. If we need to take more, we'll just say anyone whose ID ends in 1 and 6 or 2 and 7. Okay? So that's a simple and very random way to get a sample. Now, here's an example of a random way that's not very good. You want to get a survey about students in the university, and you wait at 7:45, and as students come in, you ask them questions. Well, what's wrong about this sample? Well, these are the students who come early. These are the students who come before classes. These are probably the better students, those who woke up early, right? You're going to get a completely different sample if you come, let's say, 8:20, and you survey students who are already late for class. And if they're late for class, and maybe they're in a hurry to get in class, they're going to give you completely different answers, or they won't even reply. They'll just keep walking, okay? So, you got to be careful how you do the randomness. Is the randomness really random? One of the better examples will be you wait in front of a restaurant and you then ask people about what they ate. Well, if you wait in front of a Chinese restaurant, you're going to get one type of answers. If you're waiting in front of an Italian and pizza restaurant, you're going to get a completely different type of answers, right? So, waiting people in front of the restaurant and asking them about what they ate in general is not a good idea. It may be a good idea if your population is the restaurant's customers, but not everybody. Let's see what else we got. Sample random, okay, well, you got some ID numbers, customer ID numbers, which are similar to student ID numbers, and Excel picks a sample, no big deal. Now, there are other additional probabilistic methods. One is systematic. So we got a sampling plan, and you choose every 5th person, or every 2nd person, or every 100th person. So you decide you're going to pick every 5th student, okay, or every 10th student, or every 10th customer, or visitor, or whatever it is, if it's in the movie theater. Okay? Stratified samples, you divide the population in different strata. The example will be, you may divide the population here in people living in the capital, which are going to be very different from villagers and farmers, which would be very different from, let's say, mountain people, right? You got mountain people here too, right? Sometimes. I mean mountain people in the country, not in the classroom. So, if you want to know about people in the country, you will have one sample from the capital, a separate sample from the cities, the smaller towns, a third sample from village farms, and a fourth sample from the, let's say, from the mountains. So you divide the population somehow naturally in different criteria. Well, here is a great, simple, easy strata of students. The easiest way to divide the students is first year students, second year students, third year students, fourth year students. So instead of doing random sample, you're going to do 20 people, 20 first year students, and maybe 20 second year students, and maybe only 15 third year students, and maybe 10 fourth year students. So you first define the strata, and then separately you will have a separate survey. Well, a different type of strata to define is, hey, you can define them into boys and girls, and then you decide separately about them. Or students arriving with a car is going to be one stratum, and students arriving with a motorcycle, a different type of stratum. You can have cluster sampling, okay, again, you divide the population into subgroups, clusters, it's very similar, don't want to get into that, that's not as interesting. Or you may have a continuous process. For example, you make coffee in one package, you make every 1 second. And you decide, I'm going to take a sample every 1 minute, or I'm going to take a sample every 10 minutes, or I'm going to take a sample every 100 minutes. Or as things get produced, you're going to get a sample 1 out of 100, 1 out of 100, 1 out of 100. Okay? So you devise some random way of doing it. After you got the sample, you need to do some estimation. Estimation is the next. So the first step is you need to get your goals, your objectives, figure out the game plan, meaning sampling plan. The second step is you gotta somehow get the data. Well, now the third step is estimation. And estimation is you assess the value of something unknown. For example, we assess what's the percentage of students with cars. So you want to assess a particular characteristic. Or what's the percentage of girls in a class? Or what's the percentage of overweight people? Well, or maybe completely different. Health stuff like a disease, heart disease. What's the percentage of people over the age of 50 with heart disease? Well, a very easy measurement and a very easy sample will be blood pressure. You put in, you measure, it takes about a minute. It's electronic now. You just wrap it up. It's very quick. It's very easy. And you can determine what percentage of the population have high blood pressure. Right? Well, now, more interesting question. What percentage of the students, meaning young people between the age of 18 and 25, who have a high blood pressure? Well, if I'm in the Ministry of Health, this is extremely important to know, okay? I mean, that will determine a lot about the future of spending, doctors, diseases in hospitals, and all the other stuff. So, the estimation is somehow you do the calculation based on the data, okay? An estimator will be the measure, or estimator is like the calculation, the formula that you use. Somehow you gotta have a formula for doing what you're doing. And then you get a point estimate. Point estimate is just one number. Let's say a simple number. 20% of students have a high blood pressure. Or another point estimate. 30% of students arrive to school with a car. Okay. Or another type of point estimate will be 15% of students have A grades or GPA 3.5 and above. Okay. In other words, how many excellent students you got. So that's a point estimate. The next one. When you use a formula, the formula may be good, the formula may be bad. One of the key characteristics of a formula that you use will be whether the formula gives a biased estimate. Biased estimate means, well, it's got very many different definitions, but the simpler definition of a biased estimate is as you increase the size of the sample, whether the estimate will approach the true value. In other words, is your calculation going to give you a exact number or not, especially as you increase the sample. So in general, you want the estimate to be unbiased. And most of the basic estimates that we use, the most basic stuff, is typically unbiased. You may have a sampling error. And sampling error occurs simply because you made a sample. And samples are by nature random. Let's say you got 1 million young people between the age of 18 and 25. You want to measure how many of them have high blood pressure. And you simply chose a sample which wasn't big enough. And the people were just random. If you choose a different sample, you're going to get a little different answer. And if you choose a third sample, you're going to get a third sample. So, as you choose different samples, the answers will not be always identical. There will be a slight difference, okay? Well, that difference is called sampling error. Well, non-sampling error occurs when the sample is not representative. The example, let's say in America will be, you try to measure obesity and you stay and interview people in front of McDonald's. Well, who are McDonald's people? People who love junk food. If they eat junk food, they're a lot more likely to be fat, okay? So, sampling those people will give you a very, very biased estimate of obese people, okay? Here's a completely different, so these people are not representative of American people. Here's another way to, there are thousands of ways to get a biased sample. You go at the stadium and you take a sample blood pressure from the people who are exercising at the stadium. Well, that's clearly, these are people who are exercising. Their blood pressure is more likely to be normal to low rather than high, okay? So you can't just go in the fitness room and these people are trying to exercise and somehow see are they obese or not obese and judge about everybody. Because these people are not random. These people are already exercising, okay? By the same way, you can't go in the hospital and get the blood sample, the pressure of let's say, sick people. Obviously getting sick people, the sample is not representative. Or if you're trying to get for the whole country, you can't just measure people somewhere in town. You gotta get some measure of the people in smaller towns. You gotta get a measure of people in the villages. So somehow your sample must be representative. And non-sampling error occurs when the sample is not really, truly representative. Okay, they give you some sampling experiment. We don't have to worry about that. Okay, here's the next thing. Suppose you're trying to take a sample, and the sample is very small. If it's very small, let's try to say the average of height. Well, we can get over here, and we get quite a few tall guys, and there aren't anybody short. So the sample will be, even though it's perfectly random, it's going to be relatively high. If I get in that corner, maybe I get a bunch of girls, and the sample is going to be very low. So when you had a very, very small sample, I got to see how many they got in here. You may get quite relatively uniform. You may get as much here or as much over there. Let's try and do the next. It actually shows the picture a whole lot better. If the sample is very, very small, let's say for your height over here, then we'll just take 10 people. You can get some people to be here and here. You get different samples and they're quite spread out. As you increase the sample size from 10 to 25, you see that you don't get these extreme values as much. In other words, you're going to get a whole bunch of them that will give you an average of 5. You're not going to get 4, you're not going to get 6. Same thing, when you take the height over here, if you just take a few people, you may get an average of 170, and that's clearly not true. Or you may get a sample of a result of 150, and that again is not true. But if you get 25 people, you're going to be getting a lot more averages of, let's say, 160. So what this is telling you is you do this sample many times. You do it one time, it gives you this. You do it a second time, it gives you this. You do it a third time, it gives you this. You do the sample 4th time, it gives you this. So as you do many samples, but the samples are small, you get a distribution. It looks like a bell shape, but you get a lot of extremes. Well, here it gets, the bell shape gets a lot nicer at 100. When you increase the sample size to 500, you see all of these are disappearing, and you get close to the true number. So here you get 5, and then you get 4.9 and 5.1. So the average is just about 5. Here it could be 4.4, you have some 5, you have some 6, you have more than 6. So it's a very simple, common sense lesson. If you just take one person, the measure is going to be horrible. If you get 20 people, the measure is going to be a lot better. But if you get 100 people, your data is going to look more, the sample is going to give you a very close to the truth. So as you increase the size of the sample, your precision increases. A different way of saying is that your estimate will become closer and closer to the true estimate. So if precision is important, you need to increase the sample size. Well, what's the problem with a high sample size? Well, the two most basic things in life. Money is in cost and time. It's all about time and money. So you can have a very good estimate of anything you want with a large sample, but are you willing to spend 50 million and wait for 5 years to get the answer? Or are you willing to spend only $500 and maybe 5 days? Okay? So there is a trade-off between the time and the cost on the one side and the quality of the estimate on the other side. Let's see what they got over here. Okay, well, it's a very good example over here. you're trying to do, we know that the true average is 5. They throw dice, whatever the score is. If you get a sample size of 10, the mean is about 501, but the error is very large. You're not quite sure. You get the standard deviation of those means is 0.8. This is a huge, it's like from 4 all the way to 6. When you increase the sample size to 25, the error gets cut in half. This is like from 4.5 to 5.5. Now when you increase the sample size to 500, the error gets 0.07. It's like 0.1. This is the same as from 4.9 to 5.1. So you can see that you can shrink the error 10 times. So the question is now in general business, common sense question, is what precision is good enough? And then you will calculate the sample size. That's probably coming a few slides down the road. Next question is, you get a sample. And based on the sample, you calculate the mean. And if you calculate the mean, now the question is, what is the distribution of the mean? What is the distribution of the mean? So you're going to have, you saw some sort of a bell-shaped. And see, we say that the sampling distribution of the mean, again, is the distribution of the means of all possible samples. So you take a sample of 30, you run 1,000 samples each time you calculate, and you get some kind of a usually bell-shaped calculation. All right, girls, hey, the two of you, one of them, join your friend. Okay, it's about time. So you get the shape. Usually the shape will look like a bell curve. Okay. And the standard deviation of the sampling distribution is called the standard error. So it's very important now, and that's probably the first thing that you have to remember and memorize, is not to confuse, because students do, is not to confuse standard deviation with standard error. Standard deviation is something completely different from standard error. In this particular case is standard error of the mean. And standard error of the mean tells you how much you can trust your estimate of the mean. Tells you the error, meaning the standard error of the estimate of the mean. So that's the first thing to do. So when you're going to have your midterm, don't confuse standard error with standard deviation. These are totally and completely different. The numbers are also very different. They could be 5 times, 10 times different. The error that you can commit can be, for statistical, business, and practical purposes, catastrophic. You can't confuse the standard deviation with standard error in the world of business, in the real world, okay? They are totally different things. So they just do different words which have the same word standard up front. And the standard error is the sigma divided by the square root of n. As n increases, the standard error, because it's in the denominator, the standard error of the mean decreases, gets smaller and smaller. If you increase the sample 100 times, your standard error will shrink about 10 times or so. About, not necessarily, about. So, this is the standard error of the mean. And the good news is that the package will give you directly the the standard error when you use the procedure. You use the procedure, it gives you the standard error of the mean directly. And it should be coming in a couple of slides. It will ask, well, what's the confidence interval coming should be very soon. All right, well, here's the standard error of the mean for that particular calculation. And you can see, with a sample size of 10, the standard error of the mean is 0.91. So, they tell you, for the uniformly distributed distribution, we found that sigma squared, meaning the variance, is 0.3, and sigma is 2.9. And now, if your sample size is 10, the standard error is going to be large, 0.9. If the sample size is 500, your standard error is going to be 0.1 or 0.129. Okay? So, basically, it will tell you, it's going to give you a range. For example, you measure, let's say, the height of the students, and you estimate that the average is 160. Well, the question is it 160 plus minus 5, or is it 160 plus minus 1 centimeter? If it's 1 centimeter, it is a very, very good estimate. If it's 5 centimeters, not very good estimate, right? Same thing. You measure the obesity, and you calculate that the number of obese students is 10%. Well, if it's plus minus 5, meaning between 5% and 15%, that's too much. You know, you can't trust it, it's not good. But if it's, let's say, 10% plus or minus 1% between 9 and 11, the estimate is pretty good. Okay. So, this is that standard error of the mean. Usually, it takes common sense to determine how good is good enough. It takes common business sense. Okay? You need to basically understand what's going on. And then I got a central limit theorem, which basically tells you as you increase the size of the sample, and the sample gets bigger and bigger. Okay? So, if the sample size is large enough, okay, then the sampling distribution of the mean will be approximately normally distributed. So, you will be expecting that bell shape. And here's the better part. As you increase the sample size, the bell shape will get narrower and narrower. The precision will be better and better, or higher and higher precision. And the second one is also a very good conclusion. The sample mean will be equal to the population mean. In other words, the sample mean is precise, is exact. As you increase the sample size, the sample mean will get closer and closer and closer to the true mean of the whole population. Okay? So that's what they call beautiful result, which makes you confident that if your sample is random enough and large enough, that your estimate will be relatively good. And you can calculate how good. Let's see. So, if the population normally distributed, then the sampling is also normally distributed for any size. That doesn't matter that much. Let's see what else we have here. Applying. Okay, well, one of the things which they're telling you here is that when you're making a calculation, you need to be careful. Are you making a calculation about one particular observation, about one particular individual? individual, or you're making about the mean of a distribution. So, is it about individual observation or the mean of a sample? Now, if it's a mean of a sample, you need to use the sampling distribution. And the sampling distribution is usually normally distributed or more commonly t-distribution. Should be coming very soon. So, you can use probability, the standard error and probability calculations. They give you some calculations, they give you some formulas. It turns out that with our software, it's actually even easier than that. It's even easier. It just gives you everything straight up. You just use one simple command. What I'll probably do in the lab is, for 15 minutes, just show you the basics where you click and how you get it and what you check. Okay? It's very easy to do. So from there, you can do some interval estimates. And I already told you about interval estimates. The average height is 160, and the question is, what's the interval? Is it between 159 and 161, or is it between 155 and 165? So what, how wide is the interval? The interval estimated will give you a range for the population characteristic. So the interval will tell you how reliable the estimate is. In terms of probability, will tell you what is the chance, in a sense, that the true mean is inside that interval. What's the probability that you're inside that interval? And that's called the confidence interval. Let's see if it's coming or when it's coming. So they tell you, if it's just one, it's 68% probability. Let's try and shoot the confidence interval. Okay, well, that's a simple example that they give you, is the following. You got some report and they say 50% of voters support a certain candidate. And the confidence is 3%. This means that the range is from 56 minus 3 to 56 plus 3. That's 53 to 59. Well, that's fairly decent, okay? And there's a good chance that indeed they prefer one over the other. Now, if the estimate was 52 with a margin of error of 4, that's the answer is not quite clear, meaning the range is from 48 to 56. So the true number could be 48, it could be 49, it could be 53, it could be 56. Now, it's important to understand the next thing. The true number could be even 47. And the true number could be 59. But this is not very likely. What is most likely is to be here. And that's the 68% chance. So there's a 68% chance that it's going to be inside. And there's the remaining 34% that is going to be either on the left or on the right. So it's actually there's 1/3 chance that it's outside, not inside. But it's a bigger chance that it's inside. Okay? So that's important to understand. Let's see. And from this interval, we get to the confidence interval. And the confidence interval is actually a range of value between which the value of the population parameter is believed to be. In other words, just what we said, from 53 to 50, whatever, 9%. That's your confidence interval. And that confidence interval, you assign to it a probability, the probability of 68% to be inside that interval, okay? And here that they write, along with the probability that the interval correctly estimates the truth. So the interval, confidence interval, tells you not only what's the range, but what's the probability to be inside that range. Of course, higher probability means higher confidence is better. 95% probability is better than 68, and of course 99 probability is a lot better than 95. Obviously, that's common sense. That probability is called level of confidence. Level of confidence. And the level of confidence is denoted by 1 minus alpha. So alpha will be, let's say, 5%. The confidence will be 1 minus 5, giving you 95%. Alpha is the probability that you make a mistake. So if you got alpha 5%, this means the chances that you made a 5% mistake, and the chance, of course, is that 95% you were right. If the confidence level is 1%, means 1% chance of a mistake and 99% right. So that's the confidence level. And the most common levels of confidence are 90, 95, and 99%. That's the most common confidence level. And the calculation is very simple. This part over there, sigma over square root of n, that's the standard error of the mean, okay? And z over there is will depend on the level of confidence. The level of confidence is the alpha, okay? Is it 95% or 90% or 99%? The level of confidence. Okay, so you get these out of a table. It's easy to look up out of a table, and a lot of times the software will just give the number for you directly. So for many of these things, you get it directly. You don't have to worry too much about it. Okay, that's the whole idea about using these statistical actors. Let's see what else they have. Okay, they do some here. Computing a confidence interval, whatever. So I got a production process, and then tell it, well, if 796 is the measured, the mean, that's the sample, and the error, the standard error of the mean is 588. Your range of the true population mean is between 790 and 801 with a 95% confidence. That's a simple example, and the software will do that for you. And they show you how it's done in Excel. We don't need to go through it again. That's already done. Let's see. Confidence intervals. Well, it's very simple. If you increase your confidence from, let's say, 95 to 99, the confidence interval will also increase. That's natural. If you need to shrink the confidence interval, you either have to reduce the confidence level or increase the sample size. And the t-distribution. T-distribution is very, 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 very similar to the normal distribution. And it works with so-called degrees of freedom. You use t-distribution when you don't know the standard deviation of the population. A lot of times, it's for practical purposes, it's almost like the normal distribution, especially when the size of the sample is significant. So t-distribution with 5 degrees of freedom is very flat with very fat tails. With 20 degrees, it begins to have a peak, and as you increase the number of degrees of freedom, you get close to the standard normal. The degree of freedom comes from how many observations you have, or how large your sample is. With a relatively large sample, let's say 50, 100, or 200, your t-distribution is almost like the normal distribution. You can use the normal distribution as a substitute. But again, the software will do that automatically for you, so that you don't have to do any of this stuff. And I think we're gonna finish up to this point. Maybe we'll continue next time, or maybe we'll have to scroll through and see the rest on your own, or maybe we'll do it in the lab. Spend about 10 minutes to finish this in the lab, and then spend maybe 10 or 15 minutes to show you how it's done.